Welcome to Skywarn, severe weather training from NOAA's National Weather Service in Bismarck, North Dakota. I'm John Paul Martin, your warning coordination meteorologist. In this segment, we'll talk about Doppler radar. Doppler radar is a very important part of the National Weather Service warning decision-making process. Here's a picture of the Doppler radar outside of your National Weather Service office in Bismarck. Doppler radar sends energy out, and it listens. Sends energy out, and it listens. On the right-hand side is inside the radome, the Doppler radar dome. This dish is 32 feet in diameter. It goes around in a circle, sending energy out and listening. Once it completes one revolution, it stops, shifts up a little bit, and goes around again. Again, sending energy and listening. Stops, shifts up a little bit more, goes around again, so that we're taking slices of the atmosphere. The energy from the radar goes out in a horizontal pulse and then a vertical pulse. This way, we can get a better idea of the size and shape of the object that was hit, and then determine if it was a raindrop, snowflake, hailstone, or dirt or smoke in the air. This is called dual pole or dual polarization, vertical and horizontal. There are different modes we operate the radar in. There's clear air mode, where on a sunny day or a day with no precipitation, the radar scans only the lowest levels of the atmosphere. During precipitation or thunderstorms, the radar is in what's called a precipitation mode, and we scan more layers of the atmosphere to give us a better idea of the extent in the vertical of the precipitation or the thunderstorm. There are a few radar limitations. The first is the cone of silence right over the radar. As a thunderstorm moves over the radar does not sample the whole thunderstorm anymore. It can't see the whole thunderstorm, so it may appear weaker. As the storm comes out the other side of the radar sees the entire storm again, and it may appear as if the thunderstorm grew stronger, even though through the cycle it did not increase or decrease in intensity. Another limitation of the radar is that the Earth is curved, and so the farther the energy goes away from the radar, the higher up the energy is in the sky. So at greater distances from the radar, the energy is at higher levels in the atmosphere. There are some gaps in radar coverage. It does not mean along the Montana-North Dakota border. It does not mean that there's no radar coverage. It means it's limited from the surface of the ground up to about 10,000 feet. The coverage is more limited, again, the farther you go away from the radar. Here's a drawing, a schematic of a supercell thunderstorm. Every thunderstorm has air that moves up. We call that the updraft, and air that moves down called the downdraft. Under the updraft, any precipitation here is being lifted up into the thunderstorm. It's falling out here under the forward flank downdraft. Again, under the updraft, the motion is upward into the storm, so very little or no precipitation falling there, rain and hail falling here under the downdraft. There's another area of sinking air in a supercell thunderstorm called the rear flank downdraft. This is what grabs the circulation out of a thunderstorm, the rotation out of a thunderstorm, and brings it down to the ground in the form of a tornado. So keep that diagram in mind as we look at this thunderstorm over Grant County, North Dakota. Again, the energy sent from the radar was sent out. The energy hit something, energy came back to the radar, and it painted a picture. Here's the scale from on the bottom of the screen, from light blues all the way up through the purples and white. This is called base reflectivity, a reflectivity image. The energy reflected off of objects and came back to the radar. Small raindrops return a little bit of energy to the radar. The radar paints them blue and green. Large hailstones, especially large wet hailstones, return a lot of energy to the radar shows those on the high end of the scale in the dark reds, the purples, and the whites. So this base reflectivity depicts the intensity of precipitation from energy returned, shows precipitation, boundaries, and non-weather targets like smoke. Most of the time, this is what you see when you look online for radar or on television. They show the base reflectivity off the lowest slice from the radar. This image is off the Bismarck radar and depicts smoke from a grass fire. The wind is from the northwest, and so the smoke from the fire near Cannonball on the Standing Rock Nation is going to the southeast, across Emmons County and into South Dakota. Again, this Doppler radar is so powerful, it can detect smoke and dirt and dust particles in the air. Another image we get off the radar is base velocity. This is showing us how fast things are moving in the wind, and we can infer from that the wind speed. If the radar determines the object is moving toward the radar, it's painted green, and if it's determined it's moving away from the radar, it's painted red. Again, green is toward the radar and red away, and so this day we have a northeast wind over the radar site. The wind is coming from the northeast and going to the southwest. Another important display off the radar is the storm relative velocity. This compensates for storm movement and makes it easier to see the wind pattern in and around a thunderstorm. In this radar image, we see the radar is off to the right of the image. It's the Minot Air Force Base radar located near Deering, North Dakota. The radar sent energy out. Energy hit something, energy came back to the radar. The radar determined the motion here was away from the radar and here was toward the radar. You can see this broad circulation away and toward the radar. If we look closer, you can see that we have these reds right next to the greens and blues. This is tight rotation, tight circulation inside the thunderstorm. This is actually a tornado. If you were near Bow Bells, North Dakota this day, you saw this large tornado. This is what you saw with your eyes, and in this image is what the Doppler radar shows. The National Weather Service, outlined in yellow here on the radar screen, had a severe thunderstorm warning for this storm, and outlined in red, the red polygon here, was a tornado warning on this storm. Again, base reflectivity and storm relative velocity can be used together to get a better idea of the storm structure in a thunderstorm. Here's our forward flank downdraft where precipitation is falling. Here's our updraft area where you see a weak area in the radar returns. Again, the updraft area. And back here is our rear flank downdraft, pulling circulation out of a thunderstorm and down to the ground. And indeed, there is a tornado in this image near Joplin, Missouri. Again, the radar is off on the right of the screen. The red is motion away from the radar. The greens and blues towards the radar. You can see this large circulation with the thunderstorm. And if we zoom in, you can see this rotation, very tight rotation. Again, away from the radar, toward the radar, right next to each other. This was a tornado near Joplin, Missouri. Again, the radar has limitations. Storms that develop on top of the radar or move over the radar may appear weaker or to weaken, when in reality they may not be weakening. Showers off in the distance that are small, the radar energy may go over the top and not even know the shower is there. The radar may not detect that rain shower. Terrain is also an issue with radar. As the energy swings around this side, most of the energy will go into this mountain and come back to the radar, and it'll paint a picture, the radar will paint a picture of the mountain and may not detect the rain shower beyond the mountain chain. But those limitations, there are a few, and they do limit the radar, but the benefits of Doppler radar far outweigh these few limitations. I want to thank you for watching, and I ask you to stay weather ready.